Meet Erwin Schrödinger, the Austrian physicist who made quantum mechanics his playground. Forget about the traditional laws of physics, he dove into the world of particles and atoms, where the weirdness begins and logic takes a back seat. He basically flipped the physics narrative upside down, checking under the bed for quantum-related monsters. Now, quantum mechanics is like that party where everyone behaves oddly, particles just don't follow the classic rules, like a cat that refuses to get off the couch until you promise pizza.
The result?
A treasure trove of head-scratching phenomena that make you question whether your understanding of reality has just been pranked. Enter the famous Schrödinger's cat. Imagine a cat chilling in a box with a radioactive substance, just living its best life.
But hang on tight.
This isn't your typical cat video. This cat's fate is wrapped in a mind-boggling concept called superposition, where it's both alive and dead, depending on whether someone decides to peek in. It's the ultimate game of hide and seek. So, how does this radical cat endangering system work? A Geiger-Müller counter is on the scene, detecting radioactive decay like a nosy neighbor, and it activates a mechanism that releases a deadly acid. The question of the day: is the cat's fate dependent on the atomic state or just a game of chance? Sounds like a plot twist worthy of a soap opera. In this quantum circus, particles can exist in a state of superposition, like your roommate who can't decide between going out or studying. They can literally be in multiple states at once, like trying to figure out if you want to stay cozy in bed or venture into the bustling world outside. It's the physics equivalent of committing to a Netflix series. But wait, observation is the wild card. The moment you look at our furry friend in the box, poof. The cat's fate is sealed. Before your gaze, it's all uncertainty. The cat is both hanging out and ghosting you. It's like waiting for your crush to text you back. Until you see the message, anything is possible. Now, let's talk about our ever-elusive friend, the electron. Its dance is represented by a wave function, describing the probability of finding it flitting about in a specific location. Think of it as a whimsical dance party, where each electron shows off its moves anywhere from 0 to 1 on the dance floor before it picks a spot and commits. Talk about commitment issues. Before we observe it, the electron is doing the cha-cha in every possible position within a region. But as soon as we whip out a measuring device, it suddenly decides to take a stand and pick a spot. This is a vivid illustration of quantum uncertainty, like trying to find your phone while you're on it. Good luck with that. When measurement occurs, we witness wave function collapse, where the electron finally decides to stop being indecisive and claims a specific position. This transition from a buffet of probabilities to one particular state is where quantum measurement gets a bit tricky. It's like your friend finally choosing a restaurant after 30 minutes of debate. It's all probabilities until someone makes a decision. And let's not forget about electron spin, which is another splendid example of wave function collapse. An electron can spin clockwise or anti-clockwise, but just like a magician, it keeps you guessing until you take a peek. It's basically saying, you can't know both. Talk about dramatic flair. Superposition in quantum mechanics is like a particle's version of a mood ring. They exist in multiple states simultaneously, each with its own probability until someone decides to interfere and smash those states together into one solid outcome. It's quantum drama at its finest, and we're all just bystanders. Our friend Schrödinger's cat is the grand champion of quantum mechanics quirkiness. The feline's possible states of being both alive and dead until someone opens the box reveal just how bizarre and counterintuitive quantum principles can be. It's a paradox that makes us question everything we thought we knew about reality, like checking your bank account after a night out. Now, take a moment to consider that macroscopic objects are made up of trillions of atoms. With so many particles throwing a wild party in there, their quantum wave functions interfere destructively, which masks those quirky behaviors from our observation. It's like trying to find your lost phone in a pile of laundry, near impossible and super frustrating. When we talk about interference in wave mechanics, it's like waves in a pool. Sometimes they mix nicely, and sometimes they get all tangled up. This is crucial for understanding why we seldom catch the quantum effects in larger objects. Imagine throwing stones in water and watching how the ripples interact. Physics definitely knows how to throw a party. Schrödinger's cat paradox hasn't just entertained us, it sparked monumental debates among scientists. Questions about the nature of quantum states and when quantum effects transition into classical physics bubble to the surface like an overboiling pot of ramen. So, the next time you think about that box, remember, it holds the secrets of the universe, and maybe a very confused cat.